Okay, so hello everyone and welcome back. I would like to continue our lightning introductions with an introduction to Romanian geometry. And what are we going to do? We're going to define a Riemannian metric first. So we begin with an n-dimensional smooth manifold. M. And associated to M, we obtain the cotangent bundle. And then what I can do is I can tensor that with itself. And I can take the symmetric part of that tensor. So what is this space? So this is a vector bundle over my manifold where the fiber is the fiber over a point is the space of symmetric bilinear forms on this tangent space. Right. And then I can ask for Romanian metric. This is a section. Which is non-degenerate. And let's unpack exactly what this means. This means that G evaluated at the point P is going to be a bilinear map on pairs of tangent vectors. Which is symmetric. And non-degenerate. And positive definite. So let me say it this way. I want it to be so this word instead of non-degenerate should really say positive definite. This is exactly what it means for the form to be positive definite. Okay, Now, if I choose a basis for my tangent space, I can represent this Riemannian metric, this inner product, by an n by n matrix that is symmetric and positive definite. So you can actually think of, you can think of this metric as a section of the appropriate bundle. You can think of it as a smoothly varying choice of inner products on these vector spaces, or you can think of this as a smoothly varying choice of n by n symmetric positive definite matrices. And all of these descriptions are equivalent. They're really saying the same thing. What is a Riemannian metric telling you? And I'm going to actually begin to write this. So we often write this G, this Riemannian metric as with angle brackets like this. And when the choice of metric is understood, is clear from the context, we'll often omit the subscript. Right, so what is this going to tell you? This tells you this inner product will give you a nice notion of lengths and areas and volumes and so on. So first of all, this tells you what the length of a tangent vector is. So the length of a tangent vector squared is, of course, given by the inner product of that tangent vector with itself. the angle between two vectors x and y will then be given by this is the formula you're used to for the angle between two vectors. The angle between two vectors is given by the ratio of the inner product on top divided by product of the lengths. And once I have this notion of length of tangent vectors and length and angle between two tangent vectors and so on, I can talk about lengths of curves. And I can evaluate the lengths of these curves using this given Riemannian inner product. Okay. So we also have notions of things like area and volume. So let me just quickly say something a little bit about that. So let's stop and make sense of what I've just written down. So if omega is an open set, we can compute the volume of that open set as taking the integral over the open set of the square root of the determinant times your standard Euclidean volume form. Now, if omega is contained in a coordinate chart, this is all well defined. If my domain is contained in a coordinate chart, there's nothing really to say. I choose my coordinates. I have now a smoothly varying family of n by n symmetric positive definite matrices. I can take the determinants of that and then take a square root. There's not really much to say. If I have, if my omega runs out, so I should say also this is well defined. It's well defined when the integral is finite. If my omega runs outside of my coordinate charts, I use the transformation law. And if you use the transformation law, you will actually see that this integrand, the square root determinant g dx1 through dxn, so here's maybe this is the g in the x coordinates. When I represent this in different coordinates, of course, I'm going to get a term from the change of variables going from the x variables to the y variables. That Jacobian in the change of variables ends up being a square root of the determinant of the change of variables. I have associated to this also something coming from the change of variables and going from the determinant from the x variables and determinant of g to the y variables and determinant of g. And this will give me exactly a 1 over the square root of the Jacobian matrix. So you see that those two Jacobian terms will cancel out, and you'll see that this integrand here is actually well defined. It's invariant under your choice of coordinates. Doesn't change at all. So this gives you a well-defined notion of volumes, and then you can use similar ideas to make sense of things like areas of hypersurfaces and so on. Okay. So we mentioned at the end of last time this difficulty, there's no invariant way to differentiate vector fields in a smooth manifold, and the problem comes with this was because there is no canonical way to identify the neighboring tangent spaces. And in Euclidean space, you overcome this by translating, you overcome this issue by translating all tangent spaces back to the origin. So let's just write out what this means. I'm going to write let's stop and make sense of what I've just written down. So first of all, this bar here is supposed to mean, so del bar is going to be my covariant derivative with respect to the Euclidean metric. And what am I writing here? I'm saying that my vector field X has components which look like X1 up through Xn. And I write that as an abbreviation, I write it XIDI like that. Similarly, I have Y in components looks like Y1 all the way up through Yn. And I can abbreviate that by saying it's Yj, Dj. There's an implicit sum going on here. I have an upper index and a lower index, so I sum over this repeated index so long as one is up and the other one is down. And where were we? Right. Then I can differentiate. So what I'm saying here is that the formula above says that directional derivative of the vector field y in the direction of x is this sum it looks like this. So now the question is, how can I make sense of something similar on a Riemannian manifold? So let's remember that we are a Riemannian manifold. We have an M equipped with a metric G. And let's actually just say let's just say that our manifold M happens to be immersed in a higher dimensional Euclidean space. This is a little bit of a simplification. It looks like this looks like a cop-out. It's not really a cop-out, so this will this will be true for some K by Nash embedding. And let's furthermore say that the metric actually comes from pulling back the flat metric. And what do I mean by that? I mean that the metric applied to any pair of tangent vectors is just the Euclidean metric applied to the push forward. So if I write this out in coordinates, in local coordinates, I'm going to have some phi. So again, I'm writing this all locally. I have, here's my manifold. My manifold might have some complicated topology. And I'm putting this into my higher dimensional Euclidean space. And if I restrict my attention to some small neighborhood, some small coordinate patch, what I find is that now the restriction really behaves like a smooth mapping from some open set, possibly a unit ball, in an n-dimensional Euclidean space into a higher dimensional Euclidean space. So this is the local picture. So in local coordinates, I should really think of this as mapping, should really think of this as mapping an open set in n-dimensional Euclidean space to Rn plus k, and I want that phi is injective, phi star is injective. This is really the same thing as saying that the Jacobian matrix of phi is an n plus k by n matrix with rank n everywhere. So then if I do that, I can write down my G in local coordinates is going to be dxi d psi j. So this is now on this side, this is just a Euclidean inner product. So here the GIJs, these are just the entries in the n by n matrix representing my Romanian metric G. Right, so this is my local picture of, this is my local picture for a Riemannian submanifold. Okay, so then I can define my covariant derivative by taking the Euclidean covariant derivative and projecting onto the tangent space. Okay, so this equation here requires some explanation. So first of all, what objects do I have here? I have vector fields defined on my submanifold. And my submanifold is really sitting in this larger space. So how do I extend X from my submanifold to the ambient space and the answer is that I'm allowed to choose any extension. It ends up not mattering which extension you choose. You choose any smooth extension. So the second thing to write down here is what does the tangent space, what does this mean? So So to understand that, we have to recall we have our submanifold. If I choose some base point over here, my copy of R3, so remember the tangent space. So here's my P. This will split orthogonally into this will split orthogonally into an n-dimensional subspace, which is tangent to my my manifold and a normal component. And this tangent projection is with respect to this orthogonal splitting. So this allows one to, this allows you to take derivatives of vector fields along these submanifolds. Okay. Now, at last, we're going to get to something to do with a little bit of geometry. All right, so let's specialize to the case k equals 1. And in this case where we have an immersed hypersurface, something where the codimension is equal to 1, in this case, we have that tangent space at any point of Rn plus 1 splits as the tangent space to my submanifold plus the span of some one normal vector. So here I can take I can choose some unit normal vector, and then I can write that normal space as the span of one single vector. Okay, and then let's split this ambient covariant derivative as the covariant derivative in my submanifold plus my normal part. And this is exactly what's left over. Okay, and I'm going to call this part the second fundamental form. And I'll remark here that classically, the induced metric G is the first fundamental form. Okay, and let's think for a minute, what is the second fundamental form? So here, remember, this is an inner product in Euclidean space. We see, so the thing to remember here is that I'm starting with a tangent vector y, and I also have a tangent vector x, and I have my chosen normal n. So the y is tangent to m, the n is normal, is perpendicular. So the inner product between y and n, this is the usual Euclidean inner product, is 0. When I differentiate that, I see that I'm differentiate with respect to the vector x. I see that 0 is equal to the sum of this first part is just my second fundamental form. And the second part is the inner product of y with the derivative of the normal in the x direction. So what I observe is that the second fundamental form is minus the inner product of the derivative of the normal in the x direction with y, or I can say that the second fundamental form is essentially minus the gradient minus the derivative So geometrically, what is this telling you? Geometrically, what is this telling you? This is telling you Geometrically, this is telling us how my immersed submanifold, my immersed hypersurface, bends in this space. So this is maybe a little bit easier to think of just with a curve. So let's think of just the case where n is equal to 1 for a minute. So here's my curve in R2. In blue, I have my unit normal. I have my choice of unit normal. And what is my second fundamental form calculating? This is calculating minus the rate of change of the normal direction of the immersed curve. Okay, so if this rate of change is 0, if the normal is not changing, my curve, my normal will not change, and my curve will only be allowed to move along a straight line. When the rate of change is very high, my normal has to move very rapidly, and so the curve actually must bend very rapidly. The curve has to have very high curvature when the rate of change of the normal is high. When the rate of change of the normal is low, the normal moves slowly, so the curve bends much less. Okay. So this is really the way you should think about the second fundamental form. So you should think of 2 as telling us how the normal vector, how much, let's write it as how much the normal vector bends after moving in a given direction. And this notion of how much does the normal bend is really the same thing as saying how much does the surface bend, because the only way the normal can bend is if the tangent space bends at the same time. When the tangent space bends, that pulls the whole surface along with it. Okay, there's one other thing I want to show here. So symmetry. Of this second fundamental form. Okay, so what do we want to prove? We want to prove that this gadget, which we've just cooked up, which seems a little bit arbitrary, but we've just geometrically motivated why it's an interesting thing to look at in the case, at least in the case of hypersurfaces. If you think about it, the case of hypersurface, the case of codimension one is not actually that special. Anyway, so this gadget we've just cooked up to measure how a hypersurface bends in its ambient space. This is symmetric. So what I want to show is that this is actually zero. And let's look at what we have here. This guy here is normal to the hypersurface. But this guy here is tangent. It is tangent to the hypersurface precisely because my vectors and fields that I'm starting with is tangent to the submanifold, to the hypersurface, precisely because I'm starting with tangent vectors and I'm taking derivatives, so I'm only obtaining linear combinations of tangent vectors here when I write this out. So the punchline is that this difference is actually zero, and what we have just shown is that the second fundamental form is a nice symmetric bilinear form. So this is a and what does it mean that it's a nice symmetric bilinear form? Therefore, it is orthogonally diagonalizable. And when I diagonalize this, this bilinear form, I obtain eigenvalues, of course. At a base point. And these eigenvalues are what are typically called the principal curvatures. And this is if you think about sort of standard presentations of surface theory, this is what you would find as the rate of change of the normal of a curve in a surface, and then you start to look at the curvature of curves in various directions, and you take minima and maxima and so on. This gives you the exact same thing. So we will discuss this more later, but this gives you at least a little bit of an introduction to local Romanian geometry of submanifolds and in particular hypersurfaces. So we will continue this more next time. Okay, thank you for listening.